Hi everybody, this is your instructor for Physics 2. We're continuing our instruction basically now online because of this virus that we were told to stay home, hopefully to get rid of it. Anyway, today is actually Monday, the 23rd of March. And I'm recording this one for chapter 27, for the magnetic field, basically magnetism. My recordings, I'll try to keep them as short as I can without having to go hopefully over 20 minutes. So anywhere between 15 to 20 minutes models. So this chapter will be divided most likely into 3 or more sections. So, and they will be all saved actually on Canvas, so that you can come back to them. What I will try to do is cover as much materials as I can in terms of these recordings and try to do examples. But when we meet online on Canvas, we will do examples in there and also clarify any misconceptions or anything that is not clarified in these presentations. So anyway, let's get started. So chapter 27 basically introduces the magnetic field, and so it's basically all about magnetism. So that's basically the new topic that we're starting in here. We never dealt with the magnetic field before. We don't know even what magnetism is, and it doesn't matter. We're going to introduce it. What I want you guys to remember from when we were talking about the electric field, if you guys remember, we said, okay, if I have a charge, let's call it Q1, located in space, and it's nailed in space, actually fixed, it's static, and I have another charge Q2, and it doesn't matter how many charges I have in here. It could be discrete distribution like what I have in here, or a continuous distribution of charges. It doesn't matter. As long as these charges are left alone, they will produce an electric field. How do I know that? I bring a test charge now here, Q. Remember in class we said 1 coulomb is going to be my test charge. And in that point in space that I'm interested to find the electric field, all I have to do is attach that point charge to a spring and measure the force, or how long the spring is going to compress or extend, depending on of course, the overall direction of the field. I took it in this direction. The force is exactly, for a 1 coulomb charge, is going to be a measure of the electric field. So every point in here in space is going to produce, every point in here is going to produce its own small contribution, and at the end they will all combine to give me an electric field in that point. Now if I place a charge in there, it's going to be subject to a force that is equal to, for a 1 coulomb, exactly to the electric field. But I said, and we argued then in class, that what if we can't afford 1 coulomb? 1 coulomb is not practical, and we come up with a charge Q. We will find that that force is not going to be actually E, but it's going to be scaled by the charge that we introduce in that place. So that's how we discover the electric field, basically. For the case of the magnetic field, it's a little bit different. And actually, we're going to use a different technique, which is a little bit more, in a sense, easier to deal with than the electric field, because all we need is a compass. And a compass, think of it as a mechanical device that always points to one direction or the other, depending on whether or not there is a magnetic field in presence or not. If I have a bar magnet, and that is another topic in here, magnetism exhibits itself into two different kinds of media. The first ones are permanent magnets, or what we call bar magnets, and that's how we're going to start with. This is an item that we can find basically all the time with us. And think of a bar magnet as basically a piece of metal. Usually it's made out of iron. It doesn't have to be. It could be made out of different materials. Actually, there are different materials that exhibit these properties. And basically, let me pull the. And basically, if it's magnetic, bring a needle next to it of a compass and see which way it points. If it points this way, then follow it and start to move the needle around. Let's place it near here, so we find that the needle starts to point this way. If I place it here, the needle points this way. If I place it here, for example, the needle points this way, and then here the needle points that way. And if I follow where all of these arrows of the needle, I will describe what is called a magnetic field. So this is a magnetic field line similar to the electric field line that we did for the dipole. Now, it doesn't matter where I put it in space. All I have to do is follow basically its location. I'm going to find a continuous line that I'm going to define as a magnetic field. Again, if I go from the north, actually it's going to give me a different contribution and so on and so forth. Now, I can think of this field line as actually extending inside and going around in here, and we'll talk about that one later on when we try to talk about the circulation of the magnetic field. Anyway, if I take this bar magnet, this piece of metal basically, and flip it around, what I notice actually is the needle also flip. In a sense, it's going to be pointing in the opposite direction from where it was pointing in the beginning. So there is definitely a properties in here for this bar magnet that distinguish one side from the other. So we call this side a north pole, and that's the side where the magnetic field starts from, and where the magnetic field ends at is the south pole. These are magnetic poles, okay? And the magnetic pole, in a sense, is some sort of a magnetic charge, similar to when we define the electric charge. It's a property basically. So, but they only come in pairs, okay? They come in north and south poles, okay, magnetic poles. The reason why we use the canvas, actually, it's not for this purpose, but rather for a different purpose. We use it for the case of the Earth in general. I'm going to come back to this right hand in here, because we're going to see it useful for our case. Anyway, the canvas was used initially for navigation in the oceans, because people needed to know where they are or which way they are headed at least, and they found that a compass will always points to the geographical north. We have to make a distinction here. This is where the north part of the Earth is. So a needle will always point in this direction. My Earth in here looks like it's it's a pear, but I'm trying to draw it in here. Everything I'm doing is by my hand. So this is a better probably Earth. Anyway, the Earth, the needle always points toward the geographical north, and the south is here. Okay, so if I follow this needle from where it's pointing from north to south, I can describe the field line of the Earth. So Earth actually is a big magnet, so similar to a bar magnet. Okay, we'll try to discover exactly what causes this magnetic field later on. But at this point, take it as is. The fact that the field leaves the south pole because the needle points toward the north geographical pole is really is the actual north for the magnetic field, and the south of the magnetic field is where the north, geographical north, is. So this is how the Earth would look like. It's really like a big bar magnet with the north magnetic pole in the south geographical pole, and vice versa. Okay. We need to basically, let me talk about other facts as far as these bar magnets are concerned before we get into the essence of the subject in here. One thing that we can experiment with and we can check is the fact that if I take two bar magnets, one with its north pointing this way and its south pointing this way, and another bar magnet that is actually in the same direction, what we note also here is that this is its north, this is its south. And if I put these two magnets next to one another, I see them that they attract one another. The two bar magnets are coming to one another. I don't need to push them to one another, and they will actually stick together. If I draw the field lines, of course, I see that the field is leaving the north side and coming to the south side like this, at least between the bar magnets. So this is how the direction of the magnetic field looks like between them. And the two bar magnets are attracted to one another. If I take a different configuration, basically, where I flip one of the bar magnets and make it point in the opposite direction, so let's leave the first one intact. So this one is north-south. Take the other one and actually flip it around so that this is its north, this is its south. What I notice in here is that the two bar magnets repel one another. As a matter of fact, the field lines are trying to leave in here, but instead of coming in here, they don't. They actually they cannot go to the north to north. As a matter of fact, if you try to push them against one another, what you will see is that there is a strong repulsion about them that becomes stronger and stronger the closer the two magnets are. So these two, they repel each other, and this is they attract each other. And this is similar to the electrical charges. So magnetic poles, actually, they behave like electrical charges. The only problem is that there is always two of them. You cannot have a single one of them. And we'll talk about that a little later on when we talk about the magnetic flux. I'm sorry, my brain drifted away because I'm still thinking about this configuration. If I take these two bar magnets and flip them again and put the south next to the north and the south next to the north in here, if I take both of them, this is still repulsive, so it doesn't matter. So the like poles always repel, and the opposite poles also attract, because if I take this two also and flip them around, it's the same thing. It's going to be an attraction between this north and that south. So this is some of the properties of magnets. Well, people were interested in trying to find out, and actually Lawrence is one of the people who actually did a lot of work in the area, and they were trying to measure these forces because it's not physics unless we measure it. So what they did actually, they took two magnets. Let's think of it, or actually a simple magnet with that curves around itself so that the north and the south are pointing in one direction. So I know exactly where the magnetic field is pointing at this point. And if I bring a charge in here, Q, and put it between them, and if that charge is not moving, it has a velocity 0, and I attach to a spring system, I will not see that it's not going anywhere, that charge. But if it were moving, the charge starts to be influenced by the magnetic field. So it seems like there is a force that I can measure in here, and that force actually is proportional to the magnitude of the velocity, to the speed of the charge, and it's actually proportional also to the charge itself. So the force, we know, if I bring heavier, or actually more charged particle, it seems like it's going to be subject to stronger forces versus a less charged particle. Same thing, a more moving charge apparently is subject to a stronger force. That's some of the properties of this force that are exerted on this charge. Now also, if I change the magnets and bring stronger magnets that I know they behave stronger, it seems like also it's proportional to the magnetic field, the strength of the magnetic field, I should say. And finally, it depends also on the direction with which this particle moves. If the particle was moving in the same direction of the magnetic field or opposite to the direction of the magnetic field, the spring does not change. I mean, there is no force. As a matter of fact, if I bring it in any direction, so if it was moving in any direction, so this is V and that is B, we notice that it's proportional to the sine of this angle between them. So if that angle happened to be called theta, so it's going to be also proportional to the sine of theta. Furthermore, the force was observed to be always perpendicular to the velocity direction. So it's not in the direction of the velocity v at all, but it's at an angle perpendicular to it, and also perpendicular to the magnetic field. So in this case, it's going to be in this direction. Okay, let me try to draw it. Let me make sure I didn't mess it up, because I want to make sure that it's correct. So actually it's going to be pointing down if the charge is negative, but if the charge is positive. So if the charge is positive, actually it's going to be down. Let me correct that. Okay. So this is where the force is going to be pointing. The charge is going to be going down in the downward direction. And basically, what I'm trying to argue in here is that this is actually a vector. This whole business in here of having to say it's proportional to Q, so that's what the force is, because it's a vector, so we have to write it as a vector. So this force is proportional to Q, is proportional also to the vector, the direction of the vector, and is proportional also to the vector B, but also it's perpendicular to both of them, and the sine theta can be recovered from the properties of the cross product. So this is a cross product. So what we were talking about actually is a cross product. B can be written this way if it is chosen in an appropriate coordinate system. So this expression here is valid only when we choose the appropriate units for B. So in other words, if we have a different measurement system B, this expression has to be modified with the conversion factor. So I'm going to talk more about the direction of this force, because it's very, very important to get that right. Okay. So what is the unit for B? In here, this is the unit for B. If I have a charge of 1 coulomb moving with 1 meter per second, okay, and I measure that it's subject to 1 Newton force, so that this velocity here is perpendicular to the direction of the magnetic field. This unit, I'm going to define it as 1 Tesla. That's in honor of Mr. Tesla, who did a lot of work in electricity. So, what is a 1 Tesla then? That fixes that constant of proportionality there experimentally. This law is experimental, of course, as a lot of the laws in physics. So the 1 Tesla is 1 Newton per, remember, a coulomb per divided by a second, that's actually an ampere meter. So that's basically what a Tesla is in SI. Okay.